Welcome back to another physics past paper video. Today we're going to talk about paper 2-1 from the October-November 2024 series. Alright, so let's get into the paper. Okay, so question number 1. Define density. So there are two ways to define density. So density is defined as mass per unit volume of a substance. Another way you can define density is the ratio of mass to volume. Density of a substance is the ratio of its mass to its volume. The clarity should be that the mass and the volume are of the substance or of an object. Figure 1.1 shows a cuboidal glass block. A student measures the mass m of the block and the side lengths x, y, and z. The measurements are shown in table 1.1. Okay, so basically we are going forward to finding the density. So remember, we need the density to be in kg meter cubed. All of these are given in centimeter cubed. So either we can convert all of them into centimeter, meter at one time, or we can do one conversion in as a volume. So 1 centimeter cubed is 1/10 raised to the power minus 6 meter cubed. So we can multiply all of three of these values and then just multiply by 10 raised to the power minus 6 at the end. So calculate the density. So this is mass per volume, which is just simply x, y, z in meters. 243 divided by 5.41, 11.09, 1.62, and 10 raised to the power minus 6. Now we have in meter cubed. 0.243 divided by 5.41 divided by 11.09 divided by 1.62 times by 10 raised to the power 6. We get 2500. And this is to two significant figures already, so we don't need to do anything. Calculate the percentage uncertainty in the density. So for the percentage uncertainty in the density, we need to add the fractional uncertainties of mass of x, because it's all of these quantities are multiplied or divided with each other, and z. Now the absolute uncertainties of x, y, and z are 0.01, and for this one it's 0.001. Okay, so I'm just going to write it so that I can copy this below. 0.243 plus 0.01 divided by 5.41 plus 0.0. Actually, you could have just used the division symbol over here, absolutely no problem. But since I have to copy this below, I'm writing it this way. And 1.62, oh no, sorry, 0.01 divided by 1.62. Right, okay. So we have 0.001, 0.243 plus 0.01, 5.41 plus 0.01, 11.09 plus 0.01 over 1.62, and once you have 0.013, this is a decimal number. To convert it into percentage, this would become 1.3%. Just simply multiplied by 100. Right, one question that may come up is why we used the centimeter values over here. So when we have, for example, 5.1 plus minus 0.01 0.01 centimeter. To convert it into meters, we would have divided by 100 both of these things. Okay, not just one, both of these things. So this would have become 5.41 times by 10 raised to the power minus 2, and this would have also been multiplied by, actually we can do this way. Both of them are multiplied by 10 raised to the power minus 2. So the percentage uncertainty or the fractional uncertainty remains the same. Okay, the true value of the density of the glass is different from the answer in B1 because of a systematic error in measurements. Suggest one possible cause of the systematic error. Okay, so there are different possible causes for systematic errors. One is the mistakes in experimental procedure. Okay. You could have incorrect calibration. So notice one thing over here. The least count of the mass is 0.01, and for centimeter it's 0.01. So for lengths, it's most likely vernier caliper used. So incorrect calibration of mass balance or vernier calipers. Similarly, you could have as possible zero errors also. Zero errors in mass balance or vernier caliper. Now, these are two different things entirely. Incorrect calibration may include zero errors, but as a whole, calibration requires what's the polynomial or a straight line difference between. For example, if we have the thermometers from 0 to 100 degrees Celsius, how does the temperature vary in between them? Is it sort of like a straight line or is it like a curve? So that is the calibration that we need to know. Alright, so that's question number 1. On to question number 2. Define linear momentum. So this is simple. Linear momentum of an object. Linear momentum of an object is the product of its mass and its velocity. Now in marking schemes you will see a theme that where they just say product of mass and velocity, but mass and velocity of what? So you have to be very specific that you're talking about an object or some mass that is moving. So a car of mass 1800 kg is moving in a straight line. Figure 2.1 shows the variation with time t of the momentum p of the car. So one thing to notice is the momentum is given per 10 raised to power 4 Newton seconds. So whatever values that we are going to be choosing over here, we have to multiply that value by 10 raised to power 4 also. Calculate the maximum speed reached by the car. So maximum speed reached by the car will correspond to the maximum momentum. So come on. Right, okay. So this is, let's see. Let's zoom in and see. 1, 2, 3, 4, 5. This is 7. And this would be 7.2. Right, okay. So max momentum. So max speed is equal to max momentum divided by mass. So you have 7.2 10 raised to the power 4 divided by 1800 kgs. So 7.2 divided by 1800 times by 10,000, you have 40 meters per second. Now notice one trend over here. So if momentum is 0, speed is 0. If momentum is maximum, speed is 40 meters per second, and also speed is 0 back over here. So effectively you can convert this into speed time graph also, or velocity time graph also. Okay, calculate the maximum kinetic energy of the car. So remember, we have two formulae for maximum or kinetic energy. If we want to use momentum, it's p squared over m. You can also use half mv squared. Both of them will give us the same answer. So let's check. Let's make sure. Maximum momentum was 7.2 10 raised to the power 4 whole squared divided by 1800. And the other one is, this one is half mass v squared. So let's see whether we get the same answer for both of them. So 0.5 times by 7.2 times by 10 raised to the power 4 whole squared divided by 1800. So you're getting 1, 2, 3, 4, 5, 6, 1.44 megajoules. Over here you have mass and velocity is 40 squared. So you see same value. So 1.44 megajoules or 10 raised to the power 6. So 1.4 10 raised to the power 6 joules. Okay. Show that the acceleration of the car at time t is equal to 4 seconds is 5 meters per second squared. Okay. So if we use the values 0 and 40 between 8 seconds, that will have the same acceleration because the rate of change of velocity is constant, because the rate of change of momentum is also constant. So acceleration will also be constant. So acceleration is change in velocity, change in time. So that is 40 minus 0 over 8 seconds. So 40 divided by 8, 5 meters per second squared. Determine the distance traveled by the car between times t is equal to 0 and 12 seconds. Now, as we said before, we can convert this into a velocity time graph also. So we have from 0 to 40, and then this is 40 at 8 seconds, and this is 12 seconds. So area under the velocity time graph, we can say, you should, if we had to make it, we would make it over here. So VT graph. So distance would be area under VT graph. You can use any other method also. So half times by base is 12 times by 40. So this would be 40 times by 12 divided by 2, 240 meters. On figure 2.2, sketch the variation with time t of the acceleration a of the car from t is equal to 0 to t is equal to 12 seconds. Okay, so over here in 8 seconds we had 0 to 40. So this was coming out to be 5 meters per second squared. Now from 8 to 12, it's half the time but same change in velocity. So even without looking, the magnitude would be 10 meters per second squared and negative. So change in velocity is the same, but it's half the time, so acceleration would be double. But you could definitely see that 0 minus 40 divided by 12 minus 8, so 40 divided by 4 is 10 or minus 10. So 5 and 10. So from 0 to 8 it's 5, and from 8 to 12 it's minus 10. And that's your acceleration time graph. And that's this question. Alright, moving forward. Question number 3. What is meant by work done by a force? It's very straightforward definition. Work done is defined as the product. Work done by a force or work done is defined as the product of the force and displacement in the direction of force. In the direction of force phrase is important, because if it's not in the direction of force, it's not counted. A block of mass m is raised vertically at constant speed. The vertical height gained by the block is delta h, as shown. Derive an expression in terms of m and delta h for the change in gravitational potential energy EP of the block. State the meaning of any other symbols that we use. Okay, so we know that, for example, if you are raising a block, obviously you're using another force also. So let's say, for example, this is the lifting force F and the weight mg is acting downwards. So according to Newton's second law, you would have sum of forces equals to ma. Sum of forces F minus mg. Why? Because we take upwards direction to be positive by convention, equals to ma. And a can be written as v squared minus u squared 2s, 2 delta h in this case. So F minus mg equals to half delta h, or m, v squared minus u squared. Now one thing to notice over here is that since acceleration is 0, that would mean that v is equal to u, so which means that F minus mg equals to 0. Now when we multiply this both sides by delta h. Okay, first let's not do this. So first let's multiply both sides by delta h. So you get F delta h minus mg delta h equals to change. This would actually result in change in kinetic energy, or just simply let's use half m, sorry, why is it doing this, m v squared minus u squared. Since acceleration is 0, you will have F delta h is equal to mg delta h. A is 0, v is equal to u. So F delta h is basically the work done, and mg delta h is the change in gravitational potential energy. So that means the work done is actually the work done against the gravitational potential energy change, and this is resulting in change in potential energy. So work done is the net change in potential energy. Okay, so therefore delta EP is equal to mg delta h. Any other symbols we used? Oh, right. So where F is, we can write somewhere over here where F is force lifting block upwards. Right, okay. And you can have the V and the U also, A also. So V and U are velocities, A acceleration, etc. Right, okay. Electric motor has an input power of 900 watt. The motor takes 1 minute to lift a load of 240 Newton at a constant speed through a vertical height of 150 meters. Resistive forces are negligible. Show that the work done by the motor on the load is 36 kilojoules. Okay, so like we showed over here that the work done, work done is basically the change in gravitational potential energy. So work done is going to be the change in EP, which is mg delta H. So 240 Newton is the weight and change in height is 150 meters. So 240 times by 150 is 36,000 joules, which is 36 kilojoules. Simple, straightforward. Determine the useful power output of the motor. Okay, now this is the work done in 1 minute. We need to know the power. So power is equal to work over time. So that is 36,000. So don't write 36 because that's in kilojoules. And time needs to be in seconds. So 60 seconds. So 36,000 divided by 60 is 600 watt. Use your answer in C2 to determine the efficiency of the motor. So the formula for efficiency we are familiar with, that it's the useful power output over total power input. So power output is 600, power input is 900. So 6 divided by 9, 2 over 3 is 0.666, which is 66.7%, or we can also write it as 70%, because we want two significant figures. Sorry, 70% would be not correct. We can write 67%, or you could also write it as 0.67 also. Both of this would mean the same thing. Okay, alright. Some of the power wasted in the motor is dissipated by the resistance of its coil. The dissipated power is 280 watt. Right? The coil of the motor is made from a wire of total length 23 meters. The wire has a cross-sectional area of this and is made from the metal of resistivity this. Calculate the current in the coil. So I squared R is your power dissipated. So we need the current, but we also need the resistor. So resistor is rho L over A. So that would be rho is 1.7, 10 raised to power minus 8, length is 23, cross-sectional area is 2.6, 10 raised to power minus 8. The minus 8 gets cancelled. So the resistance that we have is 1.7 times by 23 divided by 2.6. 15.038 ohms. So I squared would be P over R, 280 divided by 15.038. So 280 divided by answer 18.619 ampere square. So I would be the square root of the answer, and that would be 4.315 amps. So to two significant figures, 4.3 amps. Okay, alright, so next question. Question number 4. Define Young modulus of a material. So again, since this is just a ratio of stress to strain, you can define it as a ratio of stress to strain. Stress per unit strain also, you could define that. So Young modulus of a material is the ratio of stress to strain to its strain. Stress to its strain. You can also say is the, instead of this, you can also write it as, let's choose a different color, stress per unit strain. But obviously, yeah, alright, right. A metal wire P that, okay, so sorry, I forgot one thing. This is when elastic limit is not exceeded. As long as elastic limit is not exceeded. Right, okay. A metal wire P that obeys Hooke's law is stretched within its limit of proportionality. That means we are talking about this proportionality. This means a straight line. And this also means it's going to pass through origin. On figure 4.1, sketch the variation of tensile force F in the wire with its extension X. So that's it. Let's try again. Right. Straight line passing through the origin. State the name of the quantity represented by the gradient and state the name of the quantity represented by area. So this is straightforward. F is equal to kx, which is sort of like y is equal to mx because the y-intercept is 0. So m is the gradient, so k is the gradient, and k is the spring constant. And the area, which is the half Fx, is your elastic potential energy or work done in stretching also. So elastic potential energy. You can also say that this is the work done. However, elastic potential energy is more like it. Another wire Q is made from a metal that has twice the Young modulus of the metal of the wire P in B. Wire Q has the same volume as wire P but has double the cross-sectional area of wire P. Two wires are extended by equal tensile forces within their limits of proportionality. Okay. State and explain how the extension of wire Q compares with the extension of wire P. Okay, so let's do some math over here to see how this works. We know Young modulus is FL over AX once you do the stress over strain formula. So notice extension is, how do we rearrange it? This would be FL EA. Okay, so we need a ratio between x of q, x of p, right? So f is constant, so f, so f basically is constant, so we don't need to write it. So f l e a, f l e a. So just to rewrite or consider the factors that they have given us. So wire Q has twice the Young modulus of the metal of wire P. Okay, so first off, what we are going to do is wire Q, we are going to write a 2 over here to say that this is twice of, this is a, right, twice of wire P, okay. Wire Q has the same volume as wire P but has double the cross-sectional area. Right, so area is also doubled. Okay. Now it all comes down to length. So how does the length come into play? So the volume is the same. We know volume is AL, and AL is equal to AL. So AQ, ALQ, P, and P. So AQ is 2 times by area of P, and this is AP, LP. So AP gets cancelled, so LP is twice of LQ, or LQ is half of LP. So in fact, you have, we will multiply this by half, and yeah, that's basically it. That's all the factors that we need to consider. So factors, F is constant, E is the same as we have done, AL done. So the ratio comes down to 1 over 2, 2, and 2. So basically 1 over 8, 1. Okay, so you can also write it as 1 ratio 8. So the extension of P is 8 times more than that of extension of Q. Or you can also say extension of Q is 1/8 of extension of P. So we need to explain this also. So the extension of wire P is 8 times more than wire P. Sorry, 8 times the extension of wire Q. Reason being that we already said extension is proportional to length and inversely proportional to Young modulus and cross-sectional area. Since extension is proportional to length but inversely proportional to cross-sectional area and Young modulus. That's it. Right, that's it for this question. Let's move on to the next. Potassium 40 undergoes beta negative decay to form a nuclide of element X. Particle Z is emitted during the decay, other than the beta particle. Equation for decay is shown. Alright, state the values of beta. So remember, when we have beta decay, beta negative decay, one neutron converts into a proton and a beta negative particle and an antineutrino. So the mass number remains the same, however the proton number increases. We have beta negative charge. You can also, since this is already negative, so this mass is 0, charge is 1 basically, and we have anti-neutrino 0, 0. So we have P same as 40, Q is 20 because one proton number has increased, mass of beta particle is 0, and S is 1. Now, you can write -1 also, but there's a minus over here written already that is implied that this is a beta negative. So we don't need to specifically write -1, but even if you write it, it won't be that big of a deal. State the name of the particle Z. So full name is electron anti-neutrino. However, you can write anti-neutrino also. But full name is better. State the name of the class of the fundamental particle to which the beta negative particle and the particle Z belong. So this is easy. The class of fundamental particle are two categories, quarks and leptons. So both of these belong to the category of leptons. Determine the quark composition of alpha particle. Okay, so alpha particle we know has 2 proton and 2 neutron. Proton has 2 up and 1 down, and neutron has basically the up up down, and neutron has up down down, so 1 up and 2 down. So let's make it like a math expression over here. So 2u plus d, and we have 2 up plus 2 down. So this turns into 4u plus 2d plus 2u plus 4d. Finally, you have 6u plus 6d. 6 up, 6 down. 6 up and 6 down. You can also write it as 6 up and 6 down also. And that's it for this question. Moving on to the next question. Question number 6. Two coherent sources X and Y of microwaves of frequency 2.5 10 raised to the power 10 Hz are a distance of 0.18 meters apart in a vacuum. There is a phase difference of 90 degrees between the waves emitted at two sources. Microwave detector moves along the line PQ, which is parallel to the line joining two sources and 2.3 meters away from it. Point O is on the line PQ at a position that is equidistant from two sources. Point A is the position on the line PQ where the intensity of the microwaves is the greatest. Explain why the position of greatest intensity is not at point O. So if the greatest intensity would have been at O had there been no phase difference between X and Y waves arriving at O. So when they arrive at O, there is a phase difference, although the path difference is the same, but there is a phase difference for them. They're traveling the same distance. However, there's a phase difference between the two sources themselves. So at O, there is a phase difference of 90 degrees. So, for greatest intensity at O, there is a phase difference between the arriving waves of 90 degrees. Phase difference of 90 degrees between, you can also say. The position of greatest intensity is where the phase difference is 0 between the waves of two sources. Okay, then that would be A. On figure 6.1, draw a cross to show the position of the point on the line PQ where the intensity minimum that is closest to point O occurs. Label this point B. Okay, so remember, at A, zero phase difference. At O, since this is like there's a 90-degree phase difference between them, so at O it would be 90 degrees phase difference. Exactly 90 degrees further from that, there will be 180 degrees phase difference from A. So this would be the point closest to O that will have intensity minimum. So this will be our cross B. Show that the wavelength of microwaves is 0.012. So frequency is 2.5, 10 raised to power 10. So we know wavelength is V over F. V is 3.0, 10 raised to power 8 meters per second because this is an electromagnetic wave. 2.5, 10 raised to power 10 hertz. So you have 3 divided by 2.5 times by 10 raised to power 8 minus 10. You get 0.12 meters. For point A on the line PQ, determine the difference in distances traveled by the microwaves from X and the microwaves from Y. So we have already shown that this is where the path difference is 0. This is where, due to that, would be 90 degrees away from it, like quarter of a wavelength away from it. So quarter of a wavelength. So path difference at A is quarter of a wavelength. So 0.012 over 4. So this divided, This is 0.003 meters. Use the formula for the double slit interference of light to calculate the distance between adjacent intensity maxima on line PQ. Alright, so we have lambda is equal to AX over D, and we actually needed distance between this, so basically that's it. So I should have written X lambda D over A instead. So lambda is 0.012, D is 2.3 meters, and A was given as 0.18 meters. Right, so simple, 0.012 times by 2.3 divided by 0.18, 0.153. So to two significant figures, 0.15. And that's question number 6. Okay, so figure 7.1 shows two resistors connected in series with a cell of electromotive force 1.5 volts and internal resistance 0.28. One of the resistors has resistance 1 ohm, the other resistor has resistance R. The terminal potential difference across the cell is 1.36 volts. Show that the current I in the circuit is 0.5 amperes. Okay, so you have to remember that the current flowing through this, that the potential difference across this is 1.36. This is your terminal potential difference. However, the same current is actually flowing through this also. And that would result in, and the potential difference across this would be the lost volts. So lost volts is your EMF minus terminal PD, and that is I times by 0.28. So 1.5 minus 1.36 volts equals to I times by 0.28. 50 minus 36 is 14, and this is 0.28. So as you can see, 0.14 divided by 28 is half, 0.5 amps. Calculate the combined resistance of two resistors. Okay, so we know the potential difference across the two resistors, and we also know the resistance flowing through them. So we have terminal PD equals to I times by combined resistance. So let's call it RC for the moment. So RC is 1.36 volts divided by 0.5 amps. So 1.36 divided by 0.5 amps is 2.72 ohm. 72. This is not recurring symbol. Right, sorry, my bad. Use your answer in A2 to determine the resistance R. So combined resistance was actually 1 plus R, and this is equal to 2.72. So R would be just simply 2.72 minus 1, which is 1.72. Alright. The circuit in figure 7.1 is disconnected and the two resistors are reconnected to the cell, now in parallel with each other. On figure 7.2, complete the circuit diagram to show this arrangement. So we know how resistors will be, they are in parallel with each other, so that is what you will have to remember. So we have like this, so this line, and this line, and this line. Right, okay, let's make it a little bit neater. Okay, to clarify, this is the junction, this is a junction, and this is your 1 ohm resistor, and this is your 1.72 ohm resistor. Okay. Explain without calculation whether the terminal PD across the cell is now less than, equal to, or greater than 1.36 volts. Okay, now this is something to see over here. Previously, the effective resistance was, RF before, was 0.28 plus the 2.72. So now it's going to be less than this value, so 0. I don't want to do this, but just to show you that this is going to be now less than this, because the combined resistance is less than 2.72. Okay, now if the effective resistance of the circuit is now lower, that means EMF is the same. So this means that I is inversely proportional to effective resistance, since EMF is the same. So if effective resistance has decreased, current flowing through the circuit or battery would increase. However, if the current has increased, see that the current flowing through the internal resistor, we can call it, that would increase also. That would increase the I times by 0.28, which is the lost volts. And if the lost volts have increased, we have already wrote this, the lost volts is equal to EMF minus terminal PD. So that would mean that the terminal PD is reduced further. So this is what we have to write about. So the effective resistance of the circuit would be reduced, which would increase current flowing through the battery, or flowing through the battery, as EMF is the same as before. This would increase the potential drop across internal resistance, across battery, due to internal resistance. Therefore, terminal potential difference would be lower than 1.36 volts. And that's the end of this paper. Hope you enjoyed this, and I sincerely hope that I was able to explain all the questions properly. If you have any questions or confusions or doubts, reach out in the comments so I may be able to help you. If you have any suggestions, also please feel free to reach out in the comments. If you like this video, give it a thumbs up, subscribe to our channel, and turn on the notifications for future updates. Meanwhile, take care. We will see you in the next video. Bye bye.